Hi guys, in this video we are going to explore the basics of determining electron configuration. In other words, what we want to do is be able to identify the specific orbitals in which the electrons live for any given atom. To do this, we're going to have to come back and take a closer look at our energy diagram that we developed in the previous lecture. So remember that we were able to construct an energy diagram that places each one of these orbitals, the different types of orbitals, different shapes and different sizes, as a function of increasing energy. So recall, as you go to higher values of that principal quantum number, the energy increases, and as you go to a larger number of loads, the energy increases. And so what we're going to do then is just focus in on the letter and number designations for each one of these orbitals to make our work here a little bit cleaner. And then I'm going to present a series of 3 rules that will allow us to build up the electron configuration for any element on the periodic table. So let's start off with our first rule. So I'm going to start putting electrons into these orbital homes. And the first rule that we are going to have to follow is that we are always going to put the electron in the lowest possible energy orbital. Now notice a couple things about this energy diagram. So the energy diagram that I've illustrated here, first, I'm putting the proper ordering, which places the 4s orbital at a slightly lower energy than the 3d. And I'm using an energy arrangement that will work for all elements on the periodic table, with the exception of hydrogen. And so I want to make a note here that if you are dealing with hydrogen, technically all orbitals of the same principal quantum number would have identical energy. But for the sake of simplicity in presenting these topics, I want to stick with this single representation of the energy diagram and build up progressively more complicated atoms by adding in more electrons to this given energy diagram. So the hydrogen atom right here, which is composed of just a single electron, is going to go into the lowest energy orbital way down here, which is a 1s. So that means that the electron configuration for hydrogen is going to be a single 1s orbital, which we're denoting those guys in red, and we have a single electron in that 1s orbital. And so what we do is we write out that alphanumerical designation for the orbital, 1s, and then we put a superscript up here to denote the number of electrons in that specific orbital. So in other words, our electron configuration for hydrogen is going to be 1s1. Okay, so to denote that nice and clearly here. So electron configuration of hydrogen, 1s1. Okay, now moving on. Let's say we move beyond hydrogen to our next simplest element, helium, where we now have 2 electrons. So now the next rule that we need in order to define electron configurations is this rule that says that no more than 2 electrons can be placed in a given orbital. Okay, so each orbital, each line here on this energy diagram can accommodate at most 2 electrons. And so the first rule, which says we're going to put that electron in the lowest energy orbital, right, was then going to be followed, and we're going to look at rule 2 and say, well, hey, yes, this lowest energy orbital, 1s, still has a vacant spot, so we're going to put that second electron right there in that 1s orbital. And as a result, the electron configuration for helium is still going to be 1s, but now we're going to have a superscript of 2, denoting the fact that we have 2 electrons now in that 1s orbital. Okay, so continuing on, and if we were to go to, say, lithium, and define the electron configuration for lithium, well, now we have a third electron. And according to rule 2, we can't fit any more in the 1s orbital. So as a result, this third electron needs to jump up here to the next lowest energy orbital, which is the 2s. And that will make an electron configuration for lithium as follows. We're going to have 1s and 2s orbitals occupied, and we're going to have 2 electrons in the 1s and only 1 electron in that 2s orbital. Hey, in our next example, I want us to look at the electron configuration of carbon. Okay? So carbon, if you look over here on the periodic table, has a total of 6 valence electrons if it's neutral carbon. So the first 2 are going to go and fill up the 1s orbital. The next 2 are going to fill up the 2s orbital. Then we have 2 more electrons. So the first one is obviously going to go into a 2p. But then there's a question as to whether or not we would put this last 6th electron in either pairing up with the first or put it in its own separate 2p orbital. And so rule 3 is going to answer this question for us. Rule 3 says that if you have the option of placing electrons in 2 or more different orbitals with the same energy, then do so. Place them in those separate orbitals before pairing them up. And the way you can think about this is, you remember these orbitals are really little electron homes, right? Would you want to share, if you're moving into a house, would you want to move into the same room somebody's already living in, or have your own room, right? Well, you want your own room, right? And electrons are no different. You know, electrons all have a negative charge, and therefore they are going to be repelling one another. By putting them in separate orbitals, you are simply going to decrease the degree of repulsion. Now, from the standpoint of writing out the electron configuration, this point, rule 3, doesn't really matter, because when we write out the electron configuration for carbon, well, once again, we have a 1s, 2s, and now we also have these 2p electrons. We have 2 electrons in the 1s, 2 electrons in the 2s, and now 2 electrons in the 2p. And so it doesn't matter, you know, the fact that they're in separate 2p orbitals. They all just get lumped together. You count them all up to denote the total number in that p orbital and put that single number as a superscript. So if we move on to nitrogen, adding in a 7th electron, we end up with an electron configuration like this, where we just increment our electron total count by 1 by putting 1 additional electron in a p orbital, again following rule 3. Okay, so on this next one, I'm giving you an electron configuration, right? And we could write this out. And what I want you guys to do is just that, write out this electron configuration, and then I want you to determine what element it is that we have provided the electron configuration for. So go ahead and pause the video and work out that solution, and then click play to see the solution. Okay, so hopefully you arrived at something that looks like this for the electron configuration. We have 2 1s electrons, 2 2s electrons, a total of 6 2p electrons, and then a single 3s electron up here. So if we add together all these electrons, we wind up with a number of 11. And so if you have 11 electrons and you have a neutral atom, then that means you must have 11 protons, which means our atom must be sodium in this case. Okay, now let's do the same thing with a little bit more complicated example. So go ahead and take this electron configuration now. I'll write out the shorthand electron configuration using superscripts, and then determine which element it is that you've determined the electron configuration for. Okay, so hopefully, once again, you arrived at a electron configuration that looks something like this. 2 1s, 2 2s, 6 2p, 3 2s, and 3 electrons in that 3p orbital. Okay, so playing the same sort of game, adding up all of the different number of electrons here, we get a total of 15 electrons, which corresponds to phosphorus. Okay, so now that we've got a hang of writing out these electron configurations, I want to bring note to this periodic table that I've had floating at the bottom of the screens for these slides. And I want us to draw out some trends that are popping up. If we go back and look at that electron configuration of hydrogen, where we're adding electrons to just this 1s orbital, right? Notice that we are dealing with an element that's way over here on the left-hand side. It's highlighted in red. And when we increase to the number of electrons 1 to go to helium, we're right over here. We're dealing with another element that I've got shaded red. Okay? So this shading of red denotes elements on the periodic table where the last electrons that we add, right, when we're filling up this electron configuration, are being added to 1s orbitals. In the case of hydrogen and helium, that's the only place we're adding electrons. Okay, and if we go a little bit higher to lithium, then once again we are placing electrons, namely a 2s electron right here, in an s orbital. So note, once again, lithium is over here, and it's colored in red. Now, when we moved up to carbon, we had to start populating a different shape orbital. Specifically, we needed to start using p orbitals. So the lithium example and hydrogen and helium all were just relied on the presence of these 1s and 2s orbitals. Now that we're going up to 6 valence electrons, there's additional 2 electrons that must be placed in 2p orbitals. Okay, so now the highest energy orbitals that we're putting electrons in are now p orbitals. Okay, and so I've denoted the carbon atom on the periodic table in orange here, and I've shaded this whole region of the periodic table to correspond to elements where the highest energy electrons that you're adding in are going to be going into p orbitals. And we saw that once again with the 3p orbitals that we're adding in for nitrogen. Okay, now I want to go back and point out one final trend, and this final trend is going to really help you in terms of quickly identifying these electron configurations. So let's go back and look at the electron configuration for lithium. Okay, so once again we've got this 1s2, 2s1. Okay, and notice that the highest energy orbital, this 2s orbital, right, we are placing only a single electron in there. So we're right here in this first column placing a single electron. Now, if we compare this to the electron configuration for beryllium, well, beryllium will have a 1s2 and a 2s2. So now we are putting 2 electrons in the s orbital, and now we're over here in this second column. So the first column of the periodic table here, right, that whole column right here, places the highest energy electron in a 1s orbital, and you'll have only 1 electron in that s orbital. Okay, and then it'll be a 2s orbital, 3s orbital, 4s orbital as you go down the periodic table. Okay, now if you look at the next column over, then you are going to be actually filling up that s orbital, whatever it might be, right, depending on which row. If you're in that first row, you're going to be filling up a 2s orbital. Okay, if you're a 1s orbital, sorry, that first row. In the second row, you're going to be filling up a 2s orbital for beryllium, a 3s orbital for magnesium, a 4s orbital for calcium, and so on and so forth. Now, similar result is seen for the p block, the elements showing over here in orange, where you're filling up these p orbitals. So in the case of carbon, we saw that we needed 2 p orbitals to accommodate these additional 2 electrons. So notice we went 2 columns in to that p orange region of the periodic table. And if we went up to nitrogen, then we needed 3 p orbitals, so we went 3 columns in. 1, 2, and 3. And so moving forward then through our examples, we can see that we have a nice, easy way to essentially read across the periodic table and determine the electron configuration. You can go 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and then 3s1 because we filled up those p orbitals, and get our sodium atom. Okay, so now using that little trend, let's go ahead and write out the electron configuration for this element here and identify what element it is we're working with. So notice that the electron configuration is, of course, going to be trivial. We're going to solve the same way we did before. Okay. But now we want to just jump right down to the periodic table and determine the element without even having to count electrons. So notice here at the end, we have our highest principal quantum number is 3. So we're going to come right down here to row 3. This is going to be our n equals 3 row. We see that we filled up the 3s1, 3s2. We filled that up. And now we're putting 4 electrons into the p orbital. So we're going to have to come over 1, 2, 3, 4. And so our element then is going to be sulfur. Okay, so then to wrap things up and kind of summarize here, right, by breaking up the electron configurations in this way and exploring how these energies are arranged, we can now appreciate why the periodic table is structured the way it is. Why we have these 2 columns poking up over here, and then the set of 6 columns over here. And it's because the periodic table is arranged so that the elements that have electrons going into a given shape orbital as their highest energy are all sort of grouped together. And so we call the elements way on the left here the S block elements, all in red, because you're putting electrons into S orbitals for the highest energy. On the middle, we call them the D block. We're not going to be focusing too much on the D block for the introductory course. Once again, I'll point you towards the more advanced general chemistry content for further explanations there. But then we will be spending a lot of time working with the P block. So S and P block will be our focus, the left and right-hand side of the periodic table. So then what I'd like to leave you with then is a electron configuration table, periodic table, where basically we're putting the electron configuration for those highest energy electrons for that entire periodic table to essentially draw out explicitly the trend that we were just exploring. So moving from left to right, we see we're moving from a 1s1 to 1s2. Then we're filling up the first s orbital, second s orbital in the second column. Okay? Over here, we're filling up the first p, second, third, fourth, fifth, and then we filled up our p orbital. Then we have to come back down here and start putting electrons into that s orbital, 3s1, 3s2, second column, and then p1, p2, 3, 4, 5, and 6. Okay? So if you cross out the principal quantum number n, all of these rows look identical. These first 3 rows, or the first 2 rows here, look identical. And I should say rows 2 and 3 here look identical. The only difference is that we are incrementing by that principal quantum number by 1. So n equals 2, n equals 3, right? But the same form. And then when we go down here to n equals 4, then we start putting electrons into those d orbitals, okay? and that'll be the discussion of future lectures that we'll get into certainly in the general chemistry content.